Hey, hello everyone. Today I'll be going over my project called ColexecDB. It's nothing but a columnar execution database. So the project is something which I've extracted from metrics fund database just to understand how a columnar execution engine works or a vectorized execution engine works. So traditionally we used to have P plus tree based databases, and there was this notion of page which holds a block of records. So by record I mean rows. So as you can see on the top, so let's say this is a row which contains three columns. Green represents, let's say, ID of type int. Red represents name of type varchar, and blue represents age of type int again. Okay, so all these rows, uh, this individual row contains all the three data, and uh, previously it was stored as a collection of rows. Okay, in the storage layer. And when we used to retrieve these rows, we would retrieve it in the form of pages. So pages could be a block of maybe, let's say, 1024 KB and things like that. And um, traditionally, we used to have this iterative model where we used to call dot next function, which would give you the next row within that block. And if the current block has already completed, then it fetches the next block, and so on and so. So here I'm using the term block and page interchangeably. So page is the term which is used for block when it comes to the memory, and block is typically used in the storage layer. So it's kind of interchangeable according to me. So for the vectorized execution engine, or in columnar model, we typically store columns in continuous blocks. So here you can see that the same row is now represented as three columns, and as you can see, the data which is in the green represents the data for the one single column. So it has like age of let's say 5 students, and this red represents name of 5 students, and then uh, blue represents age of 5 students. Sorry, green represents ID of 5 students, and things like that. So in this model, as you can see, uh, the column is the primary unit, or like basically all the operations will be performed on column. Okay. So this model is generally preferred in OLAP-based databases, or OLAP-based databases, because when you want to do an aggregate operation on just one column, then it's better to just read those column values rather than reading the whole set of rows which are involved. So this project is minor, or like I'll try my best to explain basic code flow of vectorized execution engine, so that maybe whenever you read another code base for vectorized execution engine, you have a basic understanding of how things are going. So this project has got a command package and a PKG package. So in the command package, I have this main class. So main class has got uh, like simple execution flow. Basically, what we are doing here is we are creating a new client, and then we are calling the execute function, which accepts an SQL statement. So here we are passing a simple SQL which retrieves the first column, which is mark 0, and the absolute value of the second column from the table 1. So to make it very simple, uh, table 1 is not actually saved inside a storage engine, or like table 1 is not persisted in a disk or something of that sort. We are creating table 1 using mock data at runtime. So the table 1 is in memory, and it's just a mock storage engine uh, which we are using. So yeah, once we execute this command, we are also passing in something called read, passing in a function to the read rows function. So here you can see that we are passing in a function which particularly retrieves the value, which is here it's ideally a batch which we are getting. So calls, it's an array of vectors is kind of a batch. So you are retrieving the values from this array of result vectors, and then finally you are calling the print. So this is the overall flow. Basically, you accept the SQL statement, then you read the rows from the result set, and then finally you print it. So that's the flow. So now we'll go into what this client is. Okay. So client starts with an SQL executor, and then it internally calls transaction executor. So I have named all the classes, Golang files with ABC prefix, just so that it's ordered in such a way that, like, if I were to come back sometime, I have a decent understanding of the code flow. So, and within the query engine, I have also named the packages having this alphabetical prefix, so that the whole flow is ordered. So let's start with the exec function. So here you can see that we are calling exec transaction, which is nothing but the underlying function. So here you can see that we are creating a new transaction executor for executing this statement, and then we are calling the exec function uh, by passing in the new transaction executor. So the whole thing, like basically, you can look into the code in detail. But this part of the code is very simple. So what we are doing is essentially we are creating a new transaction executor and then passing in that function. So if at all during the execution we get an error, then we roll back, and if it's successful, we commit. So both this rollback and commits are just not implemented yet, but then yeah, for the sake of simplicity, for the sake of simplicity of this project, we keep it very simple. Like we don't implement all the unnecessary functions. We just focus on the main working. So before I go further, I'll just show you what the output would look like. So here you can see that we have the mock 0 and mock 1 outputted. So the mock 0 is a set of negative numbers, and mock 1 is also a set of negative numbers. Let me just show you what would be the result of mock 1. So as you can see, if we were to print mock 0 and mock 1, it would just print negative numbers from 0 to 8. So if we were to use ABS of mock 1, then we would get the positive numbers on the second column. And just a note, here we are creating batch of three records. So 0 to 1, 0, 1, 2 forms one batch, 3, 4, 5 forms another batch, and then 6, 7, 8 forms the third batch. It will make sense once we start uh, going further. Okay. All right. So yeah, as I was telling, we create a new transaction executor, and so this is the main logic for like it's more like the main flow of the uh, functions. Okay. So we start off with parsing the SQL statement. So in the parser, we are calling a library. I think the library is a, parser which is extracted from TiDB and this. So yeah, essentially we are passing in the SQL and then we get back an abstracts in that tree. So STMT is going to be an abstract syntax tree. And then we are creating a mock table schema. So here you can see that we are creating mock table definition. So we are passing in argument 2. Essentially, it means that it creates a mock table of two columns, and the first column is going to be of type in32, and the second column is going to be of type in64. And essentially, I'm just creating a schema or a table definition, and then appending both the columns as column definitions to this thing. And in this catalog.new mock schema context, what I'm doing is essentially this is the schema of the entire database. So it will have a list of tables, and apparently this class will be used to uh, resolve the column type of a table name and column ID and stuff like that. So just note that uh, it's kind of the schema, so it will hold the it will hold the list of all the table names and the corresponding table definition, and then it will have two functions: this resolve call type, resolve call ID. So essentially, these functions will resolve the column type within the database table name, and if you specify the column name, it will give you the column type for that particular column. And same goes with the ID. IDs, I think it's more likely the position within the column definition ordering. Right, so coming back, yeah, so basically you're creating a mock schema context, and you're appending table one with the corresponding table definition here. Okay. Okay, so this is the part where like the SQL statement gets converted to a logical plan. So here in the logical plan package, we call the build plan function. So it accepts the abstract syntax tree and creates a naive logical plan from it. Okay. So once the naive logical plan is created, so typically this naive logical plan is created using a package called Plan Builder in most of the databases, Golang databases out there. So once this naive logical plan is developed, we pass it to the optimizer. So right now I haven't implemented the optimizer. Like actually I haven't extracted the optimizer from the metric function database because I think optimizer on its own would be a separate project rather than making it part of this project. I just kept it outside of the scope. Okay. And then we have this physical plan. So yeah, I think once we have the logical plan, we are not doing the optimization. So this is the part where we convert physical logical plan to physical plan. So we create a new process. So process is more likely the uh, like a thread or a process, OS thread or a process which is going to execute your plan. And yeah, so we are creating a new physical plan. The next thing that we are doing is so we have this fill function. So fill function is going to be the one which will just yeah. So fill function is something which is going to be um, used as a helper function for retrieving the final batch result, and then this batch. Once we pass in the fill function, apparently all the output would be duplicated and copied into this patches, and then finally we set the result dot patches here. Okay, and yeah, this is the part where the logical plan gets compiled into a physical plan, and when we call the physical plan dot run, it starts to get executed. So this is the overall flow. So basically, we start off with the parser, creating an abstract syntax tree. We create all the tables, mock table definition, and then create a mock schema context, and then link the table name with the table definition. I think it should be named as table def. Okay. And then we create a logical plan from the abstract syntax tree node, and we skip the optimization. Uh, if we had the optimizer in place, then this logical plan would be optimized further based on a series of rules. Then we convert the logical plan to a physical plan, and then we run the physical plan, and then finally we copy the result batches onto our batches by using this fill function, and that's pretty much all we do. So I think in the main you see what we are doing is essentially from the result dot patches that we set here, we are reading back the result by calling the apply function. So in the read rows, as you can see, we have the call one and call two. And then we are basically calling, we are passing a function to just copy the contents from the batch to this two slices. Then call the print function to just print out those two columns in a tabular form. So that's the overall process out there. Now we'll look into the more interesting part, which is the query engine. So before we start query engine, I just wanted to make sure we understand the context correct. So in the columnar execution engine, column is the primary or the most granular thing. So in that particular, the right term to use would be vector. Okay, so uh, two important things are the type system and the vector. Okay, so we have to define all the types which is going to be used in our database. So here we have defined in 32 and in 64. These are going to be our types which will be uh, used in our queries and storage. And I think these are a couple of helper function to just print and things like that. So this is fine. So vector is going to be the column, as I told you. So we have for each vector, we will specify the type of the vector, and call is going to be the data which is uh, stored in that particular column. Length is going to be the length of the vector. It can also be found by using length function on the call. And then NSP is something called null bitmap. Yeah, null bitmap. So here we are using roaring bitmap. It is used to store the null values in the vector. So if a column is having three rows and out of which two of them are nulls, then you will only store the first row in this uh, the first entry in this call, and then the rest two entries would be saved as nulls in this NSP. Then we are creating a new vector. Then this append is going to uh, append a value onto the column or the vector. So it's going to be appended on the call, and yeah, I think this is pretty straightforward class. Uh, then we have something called batch. Batch is nothing but the whole table as such. So we had vector representing the column, and batch could be a list of vectors with the attribute name. So attribute name will be the column name. Then vectors is going to be the whole column data. Okay. Uh, that is about it. So as I was telling, parser is right now we are using this parser library, and we are using specifically TiDB parser uh, because I think we wanted to have more control on the, or we wanted to fetch let's say function arguments or something of that sort. For that particular use case, I think TiDB parser was more. For this particular use case, I think TiDB parser was more beneficial. In this library, we have both the with this parser and the TiDB parser, so we are using the TiDB parser. Yeah, so the primary reason why I have implemented or extracted a parser from the core project was that parser is something that's another primitive thing, so or a project on its own. So if I wanted to implement a parser, I will do it in a separate project. But then for now, for the sake of simplicity, we are using a parser which is readily available. So as you can see, we are calling the parse statement function from the parser, and it will be returning a statement. So it's, as I was telling, it's a abstraction tree dot statement mode. So the next thing is process. So process is just a execution unit. So it will have its own registry. So sorry, it will have its own register. So register is going to hold the uh, batch information and stuff like that. Okay. So process can also have the cancel context. Cancel function. So that maybe if a process terminates, it can call the cancel function, and then we can avoid further executing the pipeline. But I think for the sake of simplicity, we haven't really implemented all this function. I think catalog is going to be the information which is going to be stored in the information schema or those kind of databases in Postgres and stuff like that. So we have the table definition, column definition, and then And here we have the mock table definition. So I think this we have already covered. This is the part where we create a mock column definition. And then the schema, I think this is also already covered. Okay, logical plan. So this is the part where we convert the statement node into a plan. So let's take an example for select. So we are creating a query plan. So I think for create we have this DDL plan. For the select we have a query plan. I think for the insert also we have query plan. But yeah, I just wanted to make a point that it depends upon the AST node time. So right now we have a query plan and we set the statement type as select. And then yeah, this is the part where we uh, where they hop through the AST statement and then select statement and then we fetch the table name. So select from, then we have the table reference, then we go over the few more attributes until we get the exact table name. So typically how I reach this expression is by debugging by putting a debugger point on the select, then just understanding where the table name was. But I think there could be a more cleaner way of doing this thing. But then for now, I'm just doing it this. And this is the part where we iterate over the fields. So let's say here we are using select mock1 and comma abs of mock2, right? So the select expression, we compare the type and then we check if it's a function call or a column name. So if it's a function call, then we create a parameter called expression function. And right now we are hard coding the value as in 64 because we know that ABS of mock column 1 will return in 64, and we have kind of uh, hard coded the output type because right now we are only running on mock column 1. And then we extract the function name, then we create the expression function base object. And from here on, we are going to loop through all the arguments uh, within that function and append that to the param.args. So here you can see that we get the column name from there. And then this is the part where we use the column index to resolve column type and column index. So as I was telling, we loop through the function arguments. We get the function column names. Sorry, we get the column names inside the function, and we pass those column names, and we get the corresponding type and the column ID. Right. So this is kind of appended onto the param.args, and finally we call the query plan.params, and then we append this param object to there. For the column expression, it's kind of relatively straightforward. We fetch the column name and then we create a param and then finally we append that to the query.params. Okay, so query plan is going to have params and the statement type as their fields. I think for the DDL plan we have right now type alone, which is DDL type, but then yeah, it depends. Right now we haven't implemented DDL plan, so yeah. Then we have yeah. So this is the expression thing. So the one that I was defining earlier, right? So expression column and expression function. Expression column is uh having two fields, type and call index. And expression function is having type, name, and args. Then plan statement is, I think this we can probably skip, but yeah, query plan is the so I think you get an idea. All right, physical plan. So this is the starting point. So we create a new physical plan and then we set the process. And when we call compile, which is kind of the part where uh, we convert the logical plan to a set of scope. Okay. So if the logical plan was a query plan, which is in our case a select, we add two instructions. So we set the scope as normal and we add two instructions. The first instruction is projection. We are project projection accepts right now query.params. So yeah, previously in the query.params we had already set up mock call one and sorry, expression call and expression function call. Then the second thing that we are setting is output. So yeah, the without this output, we'll not be able to fetch results from the final results from the execution engine. So we are right now appending two instructions, projection and output. And yeah, the data source is a mock storage engine. So here you can see that we are passing in the attributes as mock0 and mock1, which is nothing but the column name that we previously defined. And then the storage engine is very naive merge reader. Uh, I'm not going in about this thing, but yeah, the basic idea is that I maintain three patches in this level one, and apparently when you call read, it iterates over the next batch and returns that. Then when you call read again, fetches the next batch until I guess three batches are complete. So that's the main idea for the mock storage engine. So yeah, finally, this RS, the uh, scope, result scope. Uh, yeah, we return the scope as output of this function. Okay. For the DDL plan, we haven't implemented it yet, but yeah, we are not covering it here. And finally, this is the run function. So what we do in the run function is uh, we call run once. So run once is going to loop over the uh, physical plan scopes. So as you can see in the for the select query, we have one scope which is uh, having two instruction projection and output. So it will loop through that. It will find that there is only one scope, and then right now we don't have any complicated query plans. So let's say in the case of join, we might have two scopes, and then both the operations would be parallelly performed, and then the result will be merged later on. But then for simplicity's sake, we don't have multiple scopes in this moment. Okay. And I think yeah, in the scope in the thread we will be calling c dot run. Sorry, yeah, we'll be calling the run function on the scope. So if the current type is normal, then we call run function. So run basically executes the scope. In the case of let's say DDL statement like create table, we'll be calling the corresponding create table function from let's say catalog, and then this will create a table for you. So yeah, a create table operation need not go through the execution engine, and it can be handled here. Yeah. So yeah, when we call run, basically it starts a new pipeline and then calls the run function there. Okay, all right. So I think now we are going into the pipeline code. Okay, so when we call the run function, apparently this is an infinite loop. So what it does is it starts reading from the storage engine. So on the first read, it fetches the first batch, and then it sets the batch in the process batch. So as I was telling, process has something called as register. Yeah, so a process has something called as register, and it has got that input batch, right? So it will set the batch on that particular register, and then it will call relational algebra dot run. So I think this is more called as ColexecDB package. So it's I think I've just renamed it as relational algebra. So yeah, the core idea is that now we call the relational algebra dot run by passing in the instructions. So and the process. So let's go to that package. Okay. So yeah, I think before that, probably there would be a place where prepare is called. Yeah, this is the part. So yeah, we call the prepare function. When we call the prepare function, apparently we are like preparing for the relational algebra. So in the case of projection, what it does is it just sets all the uh, input parameters for the particular relational logic operation. So there are two relational operations defined as I was telling, projection and output. So for the projection, we have mainly, I guess, three arguments. So the first thing is, yeah, two arguments. One is projection executors, and then the other thing is logical expressions. So just a second. Yeah, so and when we call prepare, so what we are doing is we are setting in the projection executors. So I think I'll go this part in a while. Uh, yeah, I'll go right now. So apparently, what it does is it just goes through all the project expressions in the particular uh, projection. So right now in the projection we have call one, mock call one, and then ABS of mock call. Sorry, in the projection right now we have two expressions. One is mock call zero, and then the other is ABS of mock call one. So the first column is a column expression, and then the second is a function expression. Okay. So we loop through the yeah. So we loop through all the expressions, and then for each of the expression we call this new expression executor. So depends upon whether it's an expression column or an expression function, we create the expression executor. Okay. So for the column thing, we are creating column expression executor, and for the function thing, we are calling creating a function expression executor. So column expression executor is very straightforward. It's just setting the column index and the type. In the case of expression executor, so initially we uh, create a function expression executor object, and then we get the type, and then we call init function. So I think init function is going to just set in the parameter result slice and the parameter executor slice. So parameter executor is initialized with the parameter number. So right now the function has got only one parameter, one argument, which is the mock call one column. So it just loops through that and then creates a new expression executor for that particular argument. So the mock call one inside the function is just a column name. So it will go here and then create a column expression for it. If it was ABS of another function, let's say ABS of square root of mock column one, then it will create another function expression by calling this thing, and then inside the recursive path, it will just create another column expression which refers to the innermost argument, and then when it comes back out of the recursion, it just creates an expression function, and then when it comes to the final outermost function, it will create the final expression function. But yeah, in our case, it will be just expression function and then column expression because we are having ABS of call one alone rather than ABS of square root of call one. Okay. All right. So here we see that yeah, we create an expression function. Now what we do is okay. So we have called the prepare, and now what we do is we call the call function. Okay. Mm, yeah, so we have called the prepare function. Now we are calling the run function. Okay. Run function, what it does is it apparently fetches the yeah, run function, what it does is it fetches the execution function from the map. So previously we used to uh, fetch from the prepare map. Right now we are going to fetch from the execution function map, and then probably we'll start with the projection call. So what happens here is uh, we loop over the projection executors, and then we call the eval function there. So when we call eval, I think okay. So when we call eval, what happens is if it's a column, it just returns the same vector as output. If it's a function, what happens is it calls the underlying call exec function. Okay. So as you can see, parameter executors, and then it calls eval function. So let's see. Or yeah. So yeah. Finally, it calls this eval function. Okay. Okay. Uh, mm, just a minute. Yeah. So what happens is apparently we go to the expression. Okay, let's go back. Okay. So here you are seeing that basically we call the overload. We create an overload object. So what this is that it has this function dot get function by ID. So this is a thing which calls the built-in list of built-in functions, which is going to be part of the SQL. So here you can see that inside the init, we are going through all the supported operators and then setting the particular function. So what happens here is we have a function name called ABS. So this is the function that we are calling inside SQL, right? So ABS of for column one, and it has a particular return type, which is going to be in 32, and then this is the overloading logic, or this is the more core execution logic. So we have this ABS function, and as you can see, it does a type switch and checks if it's an in32 or an in64. If it's an in32, then we so apparently if it's either of them, we call the ABS generate function. We pass in the type as fixed size D. I think fixed size D is a combination of in32 and in64. Okay. So let's say if the cardinality of MSP, which is I, what it means is if there are no nulls, if the cardinality is zero, that means that there are no nulls. Then we are in a safe position to vectorize this operation. So we can uh, probably use some assembly library to vectorize ABS calculation. ABS is a simple example. Maybe if at all, if we were to use, let's say, square root or something, then maybe we could have factorized this operation. But yeah, honestly speaking, I have never used this SIMD, so I'm not sure what are the operations supported by it and not supported by it. So yeah, I'm assuming that ABS could be done on vectorizing like SIMD operations. Okay. If any of the entries is null, in that case, right now what I'm doing is basically I'm calling the ABS function, math ABS function. I'm iterating through all the vectors, and then oh sorry, I'm iterating through all the vectors, and yes, I'm setting, let's say if it's a null, then I'm setting it as null is true, and if it's not a null, then I'm converting it using mat.abs and then setting the value as value and then setting null as false. Okay, so this is the code logic for ABS. And yeah, apparently in here we define this function, eval function, in this uh, expression field, and this gets called when we call the eval for the function expression executor. Okay. So as I was talking about, let's say if we were to have a factorized logic for ABS, then we could just put it here. So basically, it just accepts a list of entries, let's say float 32 or float 64, and then outputs a list of the same slice, but with the ABS output. So I think this marks a completion of the overall flow. Maybe I'll summarize it in a while. Yeah, this we have already gone through the storage engine. That's pretty much it. So Overall, what happens is in the client we call the transaction executor and transaction executor. So the core granular unit of columnar execution engine or vectorized execution engine is the type system and the vector. We define all the types for the uh, columns, and then in the vector, uh, vector is nothing but the representation of column, and batch is going to be the representation of the whole table, which is nothing but a group of columns. And then we start off with the parser, converting string SQL into AST nodes. This AST node is now, uh, and we create a process. Process is going to have a register which will hold the current batch. Then catalog is something that is going to be uh, condensed inside the information schema table of databases. So it's pretty much table definition and column definition, things like that. So parsers AST statement node is converted to a logical plan in this package. This logical plan is now converted to a physical plan by accepting the new process, and the logical plan from the previous stage. Then finally, we spin up something called as pipeline. Pipeline is basically going to infinitely read the contents on the storage engine and then apply the relational algebra. So relational algebra is going to be in our case projection and output. So projection is going to create a column expression and a function expression. Column expression is pretty straightforward. It will return the vector as it is. For the function expression, it will call the get function by name, and then basically it links to the corresponding list built-in function and applies that particular function logic on top of the vector. And if at all, if the vector is not containing nulls, maybe we have a good possibility of factorizing that thing, factorizing that operation. And that's the overall flow for the storage engine. Right now, we have 3 in-memory batches. Whenever we call next, we fetch the next batch, and we increment some sort of a pointer to just maintain the batch number that we have read so far. So in this way, we have seen how a basic vectorized execution engine code flow looks like.